Hi, I'm Miss Hearn. Welcome to my channel. Remember to like and subscribe. In graph theory, a cycle is a graph made up of a series of connected edges. A cycle begins and ends at the same vertex without visiting any vertex twice. Cycles are categorized by the number of edges that they have, just like polygons. So for example, the graph on the far left could be referred to as a triangle because it has 3 edges. The graph in the center could be referred to as a quadrilateral because it has 4 edges. And the graph on the right could be referred to as a pentagon because it has 5 edges. You can also refer to a triangle as a threegon, a quadrilateral as a fourgon, and a pentagon as a fivegon. In general, a cycle with n edges is called an n-gon. A cycle can be given a name by listing the vertices in order. You can begin by listing any vertex. For example, I could start with the vertex H, then list the next adjacent vertex. And it doesn't matter which direction you go. I could list I or J next. I'm going to go with I. Next to I, we have N. Next to N, we have K. Next to K, we have J. And finally, we return to H. We don't list H because it's already been listed. Then we're going to put parentheses around our list of vertices that are separated by commas, and we have one of the many names for this cycle. Let's find one more name for this cycle. Suppose that we started at vertex K and we went counterclockwise this time. So we would go to N and then to I and then to H and then to J and then back to K, but we don't need to list K twice. So this would be another name for the same cycle. If you look carefully at the 2 names, you'll see that you have the same sequence of letters, although in one case it goes from left to right, and the other goes from right to left. For example, here you see I, N, K, and down here we see I, N, K, with each pair of letters representing a pair of adjacent vertices. You also have to remember that the letters on the ends are adjacent as well. When we're trying to determine if a graph is a cycle, it's not always very obvious depending on how the graph is drawn. One way to check if you have a cycle is to analyze the graph to see if it has 2 characteristics. 2 characteristics that all cycles have are that the cycle has the same number of edges as vertices, and each vertex in a cycle has degree 2. For example, in graph A, there are 1, 2, 3, 4, 5 vertices, H, I, N, K, and J. And there are 1, 2, 3, 4, 5 edges. So it satisfies the characteristic of having the same number of edges as vertices. The degree of a vertex just means the number of edges that meet at that vertex. If you look at vertex H, we see that there are 2 edges meeting at vertex H. So vertex H has degree 2. So does vertex I, vertex N, vertex K, and vertex J. So this graph satisfies both of these characteristics. It's a cycle. Let's practice identifying whether a graph is a cycle using graphs F and Q. So you can probably tell looking at graph F that it's not a cycle, but you can confirm it by checking the 2 characteristics. For example, we know that a cycle has the same number of edges as vertices. So let's confirm whether graph F has that characteristic. We have 1, 2, 3, 4, 5 vertices. Let's see how many edges. 1, 2, 3. Only 3 edges. So this is definitely not a cycle. It fails the first characteristic. Let's see if it fails the second characteristic as well. Keep in mind, it only has to fail one of these 2 characteristics for us to know it's not a cycle. So each vertex in a cycle has to have degree 2, and we see that Vertex F is degree 1, vertex G is degree 2, vertex H is degree 1, vertex I is degree 1, and vertex J is degree 1. So definitely not all degree 2. There are two concrete ways to explain how we know that this graph is not a cycle. Now let's look at graph Q. First, let's check to see if it satisfies the characteristic of having the same number of edges as vertices. We have 1, 2, 3, 4, 5 vertices, and we have 1, 2, 3, 4, 5 edges. So we satisfied the first characteristic. Now let's check the degrees of each of the vertices. There are 2 edges that meet at vertex Q. There are 2 edges that meet at vertex O. There are 2 edges that meet at vertex N, 2 that meet at vertex M, and 2 that meet at vertex P. So this graph satisfies the second characteristic of a cycle. As long as it satisfies those 2 characteristics, we know that we do have a cycle. In this case, there's also another way to know that we have a cycle, which is to stretch the graph into a different layout. So I could keep vertex Q at the top, but move vertex O to the side, maybe put vertex N over here, M over here, and P over here. Now remember, all that matters in a graph is not how the pieces are laid out, but what is connected. So Q needs to be connected to O, Q needs to be connected to P, O needs to be connected to N needs to be connected to M, and M needs to be connected to P. And now it's more obvious that we have this kind of circular route through the graph called a cycle. In this example, we're asked to determine if each of these graphs is a cycle. If it's not a cycle, we have to explain how we know it's not. And if it is, we have to categorize it, which means tell what size it is, and name it, which means to list the vertices in order. Let's start by checking to see if graph B has the characteristics of a cycle. One of the characteristics is that the number of vertices is equal to the number of edges. You can quickly see that there are 8 vertices in graph B, and there are 1, 2, 3, 4, 5, 6, 7, 8 edges as well. So far, so good. Now let's check to see if this graph has all vertices of degree 2. Vertex 1 does, vertex 2 does. In fact, all of the vertices have degree 2. So this is definitely a cycle. Since it's a cycle, it can be categorized by the number of edges. Remember, there were 8 edges. That makes this an octagon or an 8gon. Now we can start naming the cycle by listing any one of the vertices. Let's just go ahead and start with vertex 1. Next to vertex 1, we have vertex 2, and then vertex 3, and then that's adjacent to vertex 4, which is adjacent to vertex 5, which is adjacent to vertex 6, which is adjacent to vertex 7, which is adjacent to vertex 8, which brings us back to our starting vertex 1. So this one could be called 1, 2, 3, 4, 5, 6, 7, 8. Now let's analyze graph C. First, let's try to determine if the graph is a cycle. We're going to check to see if the number of vertices is the same as the number of edges. Once again, we can see very quickly that we have 8 vertices numbered 1 through 8. The number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges. So this is not a cycle, and a justification we could give is that the number of vertices does not equal the number of edges. But that's just one option. We could have also checked the degrees of the vertices, and one thing that stands out to me is that vertex 2 has a degree of 3, as does vertex 6. And if you have even one vertex that's not degree 2, then you know that you don't have a cycle. Now let's go back to graph B for just a moment and observe that all we really need is the name of the graph in order to get a full description of it. Remember, in graph theory, all that matters is which vertices are connected to each other. So I can put 8 vertices, and then I can use the name of the cycle to connect the adjacent vertices. 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, 4 is connected to 5, 5 is connected to 6, 6 is connected to 7, 7 is connected to 8, and of course 8 is connected back to 1. Although this isn't in the same format as the original graph, you can imagine picking up vertices like vertex 4 and stretching it over here and expanding this whole thing into a great big octagon without ever having to disconnect any of the adjacent vertices. So they really represent the same relationships. So to summarize, a cycle is a graph made of a series of connected edges. A cycle begins and ends at the same vertex without visiting any vertex twice. Cycles are categorized by the number of edges, and a cycle with n edges is called an n-gon. You can name a cycle by listing the vertices in order, with commas in between and parentheses on the outside. And you can identify any graph as being a cycle if you confirm that the graph has the same number of edges as vertices and that each vertex has a degree of 2. I hope you found this video helpful. If you did, please give it a thumbs up. That will help other students to find the video. You can also subscribe to my channel, Miss Earn Mathematics, for more math videos.